first, let's have a quick look at what happens when charge flows around a circuit. We have a voltage or potential difference, which is a push given by the battery. It sends the charge around the circuit. The charge goes through all parts of the circuit here and comes back here. As it travels round, it releases energy to the light bulbs. So the battery voltage, the potential difference, gives the energy, gives the push, and it gives it like energy. Can you imagine coal going in the wagons of a train that go round? Each unit of charge is like a train wagon, like a carriage in a train that carries coal. The same train goes all the way round, but on its path, on its way round, it releases some coal, some energy, which is used by this bulb. Some is released by this bulb, and some is used by this bulb. The flow of the carriages is called the current. And this is basically the way it works. The interesting thing is that people make mistakes thinking the current is going to be one value here and different there and different there. It's the same train that flows all the way through. So in other words, it's the same charge. The current in a single loop is going to be the same at all points. The energy gets lost as it goes round, but the charge will still be the same. Define electric potential difference. Now, the electric potential difference is a measurement of the difference of potential energy, or kinetic energy also, of a single unit charge. So it's basically the energy difference per coulomb, per unit charge. And this is the way we express it. PD is the potential difference, energy is the energy in joules, and charge is the charge in coulombs. So the voltage equal to or potential difference is the energy divided by the charge. Or, yes, exactly, E over Q. Define electric potential difference. Now, if we have two plates, this is a positive plate, this is a negative plate, and there's a potential difference of 12 volts. What it basically means is that when 1 coulomb travels from one side to the other, and the potential difference is 12 volts, it will gain 12 joules of energy. As it moves across, it gets faster and accelerates, and it will gain 12 joules of energy, which also means it will lose 12 joules of potential energy. So it gains 12 joules of kinetic energy, which means it loses 12 joules of potential energy. So 12 volt means basically 12 joules for each coulomb. Determine the change in potential energy when a charge moves between 2 points at different potentials. Now this is a potential of 100, this is a potential of 40. What is the potential difference between the 100 and 40? The potential difference is 60. It's the difference that counts. Now, so when 1 coulomb moves from left to right, it will gain 60 joules of kinetic energy, which means it loses 60 joules of potential energy. If you push it back the other way, then you're pushing it against the electric field, which means that it's going to gain 60 joules of potential energy. When it goes from right to left towards a positive charge, it gains kinetic potential energy, which means it loses kinetic energy. Now we need to define the electron volt. This is a very convenient way of representing energy. An electron volt is a unit of energy. And it's defined as the changing energy when 1 electron is moved through a potential difference of 1 volt. In conventional units, we can find out how much that is going to be. You know that the energy, because the potential difference is the energy divided by charge, the energy is equal to potential difference times by charge. The potential difference is 1 volt, the charge is the charge of 1 electron, which is 1.6 times 10 to the minus 19 coulombs. This gives an energy of 1.6 times 10 to the minus 19 joules. This is what 1 electron volt is. However, we're going to use a more convenient unit derived from the definition. So the electron, the energy, and instead of joules, we have it in electron volts. It's still the same equation, potential difference times by charge, but it's going to be 1 volt, with potential difference, times by 1 charge, which is 1 electron charge. So the unit is going to be eV. So it's going to be 1 electron volt. 1 electron volt is the same as 1.6 times 10 to the minus 19 joules. This is a measurement of energy, and it's a derived unit from the formula that we use. We use derived units in other examples in physics. For example, this is a conventional unit. The energy is equal to power times time, and we have a 2000 watt heater on for 2 hours. It's going to be a very complicated number, a very large number. 2000 times by 2 hours in seconds is going to be 2 times 60 times by 60. So we end up with a very clumsy value, 14,400,000 joules, which is not very convenient. But if we define a new unit according to this formula, we have the power, instead of in watts, we could have it in kilowatts, and we have the time in hours. We make a new unit, which is kilowatts times by hours, which is called the kilowatt hour. So power times time, power in kilowatts, time in hours. We have 2 kilowatts times 2 hours, gives us 2 times 2 is 4 kilowatt hours. It's a much more convenient unit, in the same way that 1 volt times 1 electron is 1 electron volt. Solve problems. The potential difference is the energy divided by charge. And we have 4 microcoulombs of charge accelerated by a voltage of 1000 volts. How much kinetic energy does this charge gain? Well, the energy is equal to the potential difference times by charge. Potential difference is 1000 times by the charge, which is 4 times 10 to the minus 6 coulombs. So that's going to be easy. We just multiply by 10 to the 3 here. So it ends up being 4 times 10 to the negative 3 joules. Notice we keep that in joules, not in electron volts, because we've got quite a large amount of charge. Another example. A potential difference of 1000 volts is used to accelerate an electron. How much kinetic energy will the electron gain? Here again, potential difference times by charge. This time we're going to use electron volts. Potential difference is 1000. The charge is 1 electron. So the energy gained is 1000 electron volts. That's easy. Another example, the photoelectric effect. What happens here is that in this experiment, we have an electron which moves up between this plate and this plate. The electron moves upwards, and there's a potential difference there. And we managed to find that the kinetic energy of this electron, when it moves across, is 4 electron volts. But we want to stop it, so we want to basically change up 4 electron volts to 0. So it loses this kinetic energy as it turns to potential energy. So in other words, how much voltage is needed to slow down the electrons so that they stop? Here has an energy of 4 electron volts, and it just gets to here, in other words, the kinetic energy is 0, which means that 4 electron volts turns into 4 electron volts of potential energy. Using the equation again, the energy is equal to the potential difference times by charge, but here we want to find that potential difference. The energy is 4 electron volts. The charge is 1 electron. So all it needs is 4 volts to stop that electron from just getting to the other side. It is sufficient for students to know that current is defined in terms of force per unit length between parallel currents carrying conductors. This is the definition of the ampere. The definition of current is basically the flow of charge, the rate of flow of charge, the change in charge divided by the time it takes. So the current is the rate of flow of charge. What this is this definition when you have 2 infinitely long wires, and they're parallel, they're 1 meter apart, and each carries 1 amp, so this is the definition of 1 amp, 1 ampere. There will be a force between them of 2 times 10 to the minus 7 newtons for every meter of that length. This is the definition of 1 ampere, and it uses the idea of the motor effect. This is why there's this force. So you've actually seen this before. So this is in the fields and forces topic.